In this video, we're going to look at adding fractions with like denominators. Use the diagrams given to represent the values in the addition problem and find the sum. Then perform the operation and represent the sum using the symbolic representation of the algorithm. So let's start by reading the question and highlighting our given information in yellow and our goal in green. So John had 1/5 of a pepperoni pizza and 2/5 of a mushroom pizza. Now I see our question is coming, so this is going to be our goal. How much of one whole pizza did John have? So we're given a diagram, and notice each one of these is going to represent a pizza. It's cut into 5 equal pieces, so that way we'll be able to represent 1/5 and 2/5 easily. And then the final circle, we're going to fill in the combined amount of these two circles to see how much of one whole pizza John had. So first 1/5, we're going to fill in 1 out of the 5 pieces. For 2/5, we're going to fill in 2 copies of 1/5 of the pizza. And then our result, for addition, we're combining these amounts. So I'll start by putting the 2 mushroom here and the pepperoni in here. So relative to one whole pizza, even though they came from separate pizzas, John had 1, 2, 3 out of a total of 5 equal pieces, or 3/5 of the pizza. Okay. So now let's connect this to copies of language and how we would write this symbolically. So 1/5 is 1 copy of 1/5. And that may seem pretty obvious or trivial, but we want to see how many we're combining together. 1/5 is the size of the pieces, and we have one copy of those for 1/5. 2/5 is 2 copies of 1/5. So combined, we have a total of 1, 2, 3 copies of 1/5, which is equivalent to the fraction 3/5. Okay. So symbolically, we'd write this. This is asking us to find 1/5 plus 2/5. Notice we add the number of copies, which is in the numerator, so we're going to add 1 plus 2. But we do not add the numbers in the denominator. We're keeping that number 5 because that represents the unit fraction or the size of the pieces. So 1 plus 2 is 3, and our result is 3/5. Before we move on to the next example, I just want you to take note of something. Students sometimes, and rightfully so, look at this diagram and they say, well, there's 1, 2, 3 pieces shaded, and there's a total of 10 pieces, so they think, well, this is 3/10. So let's put 3/10 question mark. Okay? And this is actually an error in this case because we're asked how much of one whole pizza did John have. So relative to a pizza, a single pizza, this is 1 out of 5. If the question was how much of all the pizza did John have, then these 2 pizzas would represent the unit, or 1. Well, then it would be 1/10 plus 2/10 equals 3/10 if we had 2 pizzas as the unit. Okay. But in this problem, it's very clear that 1 pizza is the unit. Okay. So sometimes in application problems, well, always in application problems, you should really make sure you understand from the context of the problem what the unit is and what represents 1. With the symbolic representation of the algorithm, this right here, this is representing this problem where we are referring to the whole pizza. So whenever you have a problem just given to you without a context, you are not going to add the denominators. Okay, the size of the pieces remains the same. Okay, so let's look at the next one. Let's highlight givens. So Christiane sprinted 3/8 of a mile and then jogged another 7/8 of a mile. And here's our question. How far did she run in total? So here we have a number line to help us represent and visualize this. And the number line is representing the number of miles she ran. So we'll put miles here. Okay. And our goal is to find how far she ran in total. Well, let's start with 3/8. So notice that the number line, I had it pre-partitioned into 8 equal pieces for the unit. So the unit is 1 mile, and this is 8 equal pieces, which you could count if you feel like it. Okay. So first she sprinted 3/8, so we have 1/8, 2/8, 3/8. So 3/8 is right here. And she started at 0 miles, and then she sprinted 3/8. Now this is an addition problem because it says she jogged another 7/8 of a mile, so we're adding on 7/8 to this 3/8. Okay, so on the number line, 7/8 is right here relative to 0, but we need to add on 7/8 to 3/8, so we're going to count 7 more from here. So 1, 2, 3, 4, 5, 6, 7. I'm going to put a dot here, and then I'll draw this. Okay, so this is plus 7/8, but in total, this would be 8/8, because 1 is 8 over 8, or any number over itself, 9/8, 10/8. So this is a good way to visualize this problem. Now let's connect it to copies of language and to the algorithm. So 3/8 is 3 copies of 1/8. 7/8 is 7 copies of 1/8. Okay, so we have a common unit fraction, so we just want to add the number of copies. So in total, she ran 7 plus 3, or 10 copies of 1/8 of a mile, which is equivalent to the fraction 10/8. Okay. So now let's write this as a simplified improper fraction and a simplified mixed number. So 10/8, I'll write this right under here. Notice 10 and 8 each have a common factor of 2. So we could think of this as 2 times 5 over 2 times 4. The 2's cancel to 1 because we're dividing, and we have 5/4. So as a simplified improper fraction, because 5 is larger than 4, it's improper, she ran 5/4 of a mile. As a mixed number, you can use the number line a little bit if you want, because notice this is 1 and 1 2/8. So 1 and 2/8, but 2/8 also is not simplified. 2 and 8 have a common factor of 2. I'm going to reduce that and let you you could do that computation on your own. Basically, 2 and 8 have a common factor of 2, so I divided 2 by 2 to get 1, 8 by 2 to get 4. Okay. Now, let's see how we'd write this with the algorithm. So we have 3/8 plus 7/8. We add the numerators. We do not add the denominators. We keep the denominator. That's the size of each of these pieces, which didn't change. And we have 10/8. And then we can rewrite that as an improper fraction as 5/4, as we've already done, or as a mixed number, which is 1 1/4. And since it's an application, we'll write that our answer was in miles.